Alright guys, welcome back to Underground Science, and in this video we'll talk about hydrohalogenation and some examples and mechanisms. Alright, so let's go and get started. So first thing we should be familiar with is the concept of nucleophiles versus electrophiles. So a nucleophile, right, is something is a molecule that's electron rich, or an area of a molecule that's electron rich. Okay, so just remember, nucleophiles are electron rich and electrophiles are electron poor. Okay, so, and we should also know that when you form a bond, like a bond between two atoms, so let's say we say hydrogen gas, like what this bond is basically electrons, right? So you have one electron that this hydrogen's giving and one electron that this hydrogen's giving. Okay, so bonds, well, it makes sense then that bonds will most likely be formed by nucleophiles, because nucleophiles are the people that are electron rich. So if someone's electron rich, they're going to want to donate those electrons in order to form a bond. Okay, so that's important to know before we start talking about hydrohalogenation reactions. And so now that we know that, let's dive into our first example. All right, so our first example will look something like this. And we're reacting this with hydrobromic acid, okay, which is a strong acid. So first of all, what would the mechanism be? Okay, because we can just memorize the reactants, reagents, and products, but it'll also help us put this into memory, hydrohalogenation, if we know the mechanism of how this reaction works. So let's say we drew both these molecules down here, okay, but a little bit smaller so we can see the mechanism clearly. And let's actually draw out the bonds too. So the main area of focus, right, first will be identifying what is the nucleophile and what is the electrophile. So right away, the nucleophile, remember the nucleophile is what initiates the bond making. So because it's electron rich, okay, so the nucleophile will want to make the bond. So right now, what's the nucleophile? This molecule or this molecule? The answer is this molecule, but specifically, it's this portion of this molecule. The reason is because a double bond, remember what is a bond? It's made up of electrons, right? What we went over in the previous slide. This hydrogen bond, right? It's one electron from this hydrogen, one electron from this hydrogen. But in this whole molecule, you have two bonds, right? A double bond. So you have even more electrons here. So this is going to be the nucleophile because this is electron rich. So this will be doing the attacking. Okay, that's what it's called. When a nucleophile tries to make a bond, we call it attacking. Okay, so this nucleophile will attack the hydrogen. All right, so let's see what this mechanism looks like. So now we know that this is a nucleophile. So these electrons, we're drawing arrow configurations, okay? So when I'm drawing this arrow, this is the movement of the electrons, okay? So where the electrons are going. So if we take this double bond and we say, okay, this will attack the hydrogen, and if you attack the hydrogen, then this bond will break, and these electrons will go on bromine. Bromine's a halogen. It's very electronegative, so if you're electronegative, that means you like having electrons. So it's good that bromine gets these electrons. All right, so if we do that, what will the next step look like? So if we draw step by step, the next thing, right, the next step will look something like this. So remember, the double bond used to be here. However, we use the electrons in the double bond to attack the hydrogen so we can make a bond with the hydrogen. Okay, so if we make the bond with the hydrogen, then let's draw the new bond in red. Okay, that's going to be the bond to hydrogen. So specifically, it was this carbon that made the bond with the hydrogen, and this bond here broke. So we have a bromide anion. Okay, so we have a bromide anion. Now, notice what happened here. So this bond, right, part of this double bond was used, so this nucleophile basically, right, this double bond area attacked the hydrogen, and so we used this bond to make this bond right here, right? We attacked the hydrogen, made a bond with this carbon. So remember what a bond is. There's one electron here, one electron here, okay? That's how you can think about it. So if both these electrons, right, went away, but what happened was this electron, this carbon kept when he made the bond with this hydrogen, okay? But this electron for this carbon was lost. It wasn't lost, it was used to make a bond with this hydrogen. So that means this carbon lost one electron. Okay, so that means if you lose a negative charge, you become a positive charge. So now this carbon has a positive charge on it. And a carbon that has a positive charge on it is called a carbocation. Okay, so let's write that down. A carbocation. So we formed a carbocation. All right, cool. Now, remember, anything that is electron poor, we said was an electrophile. So that means this carbon is just waiting to get attacked by an electron-rich molecule, or else known as a nucleophile, because it's electron poor. So, right, you can think of this as a p orbital here, right? This is basically an empty p orbital that's electron poor, so it's a really good environment for someone that's electron rich to attack it and make a bond with it. So in the next step, what's going to happen, right? If we just drew the arrow down, redrew this real quick, then this is the bond that was made in that step. Then we have the bromide anion here, and then we have the positive charge here. So the next step, what's going to happen is this bromide anion is going to come here and attack that carbon. Okay, so now what's going to happen is, remember, attacking, what does that signify? This is the movement of the electrons, this arrow. Now if I'm drawing this arrow and it ends here, that means this bromide ion attacked this carbon, means it made a bond with this carbon. So that's going to look like this now. So if we draw the next step, we're going to have something like this. All right, and then we're going to have, remember, the bromide ion attacked this carbon, so that's this carbon. So now this carbon, right here, will have a bond to bromine, okay? So let's draw this. Actually, let's draw this a little bit lower really quick. So if we drew this right here, right, drew all the bonds, and then we're going to have a bromine atom right here. So see, this bromide ion attacked this carbon and made a bond. Okay, and actually this is the product. This is the answer that we have. But something you guys might be wondering is, when this double bond, this nucleophile, right, attacked the hydrogen, why did this carbon bind to the hydrogen? Why didn't this carbon bind to the hydrogen? So what I mean by that is, when we draw this again, right, this is an important concept to know. And we draw this right here. When we attack this hydrogen, we made it so that this carbon right here is the one that was bound to the hydrogen, and the carbocation was over here. But why can't this happen, right? So let's draw another color. Why can't this happen? So the double bond is here. We have the HBr here, right? When this attacks, why can't this hydrogen, so let's redraw it. Why can't this hydrogen be the one, or this carbon be the one to bind to the hydrogen, and this carbon have the carbocation? And that's when we start talking about Markovnikov versus anti-Markovnikov. So if we take a look here, right, if the hydrogen binds to this carbon and the carbocation comes here, we talked about this in a previous video. If the carbocation is on this carbon, right, what level carbon is this? So is this primary, secondary, tertiary, or quaternary? So remember, if a carbon is bound to two other carbons, that's a secondary carbon. So if this carbon is a secondary carbon and you have a cation on it, that means this cation is a secondary carbocation. Same thing goes with here. If this attack happens and the hydrogen were to bind on this carbon and the carbocation were to come on this carbon right here, right? What level carbon is this carbon right here at the end? This carbon is only bound to one other carbon. So this carbon is a primary carbon, but there's a cation on a primary carbon, so that means this cation is a primary carbocation. Who is more stable, a secondary carbocation or a primary carbocation? The answer is a secondary carbocation, right? So that's why you would prefer the hydrogen to come on this carbon so that you can get a carbocation on a more stable carbon, which is a secondary carbon. So if a carbocation comes on a more stable carbon, so a higher level carbon, so secondary versus a primary, this is called Markovnikov addition, okay? So we're adding the hydrogen so that the cation goes on a more stable carbon. This is referred to as Markovnikov. But this can also happen right here. This can also happen where the hydrogen is added so that the carbocation is on a less stable carbon, that being the primary carbon, and this is called anti-Markovnikov addition. Okay, anti-Markovnikov addition. Okay, and so, but we always want the Markovnikov addition because that's more stable, right? Because the carbocation is on a more stable carbon. But there are many examples where you can do anti-Markovnikov addition. We'll go over that in a future video and its mechanism, which is pretty interesting. But for this, right, so if we drew our initial problem that we had, which was you react this with HBr, and we found out that the product was something like that, in which you added the hydrogen over here, and the bromine got added on the more stable carbon, a secondary carbon, and so that was our answer. Okay, so if we go on to another example though, let's go to another example real quick. Let's say we had something like this. Again, this was a hydrohalogen, hydrochloric acid, another strong acid. So by now we should know the mechanism, so if we drew the mechanism down right here, and we drew HCl, again, what's the nucleophile? Wherever it's electron rich, which is a double bond. This double bond will try to make a bond with the hydrogen by attacking it. This bond will break. The electrons will go on the chlorine, the more electronegative atom, which is good, because electronegative atoms love having electrons. So the next step will look something like this. And this will be bound to a hydrogen. Let's make that blue, indicating that's the new bond. And then you're going to have a chloride anion. Because this carbon lost one electron, right? Because this bond is made up of 2 electrons, that means that this carbon will have a positive charge on it. So it's a carbocation. And again, this carbon is the one binding to the hydrogen, right? Because that will make it so that this more stable carbon, a secondary carbon, will have the cation on it. We don't want this carbon to have it because that would be a less stable carbon. This is a primary carbon. This is a primary carbon. We want the cation on a secondary carbon if we were comparing it to a primary, because the secondary is more stable. Okay, now this makes a good, remember, this indicates that there's a p orbital here, right? A p orbital, an empty p orbital with a positive charge is basically a really good environment for something that's electron rich to come and attack and make a bond. But because, one thing to note here is because this is an empty p orbital, this chlorine can either attack from the bottom or from the top. It can do either or. So we can end up with, right, that's the hydrogen. We can end up with the chlorine attacking from the top, right, so a wedge bond that's coming at us, or we can end up with the chlorine attacking from the bottom, which would be a dash bond, which means this bond is going away from us. And that's basically it, guys, for hydrohalogenation. But the examples covered in this video were like more of the simple examples of hydrohalogenation. In the next video, we'll go over more tricky examples in which we have to watch out for carbocation rearrangement, so like methyl shifts and hydride shifts, and a lot more cool things. All right, so I hope to see you guys there.